Okay, so good evening, hello, and welcome everyone to week 4 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. The course is being offered by NPTEL. It's currently being taught by Professor Amaresh Dalal from Department of Mechanical Engineering, IIT Guwahati. I'm Debjit. I'm a PMRF scholar at IIT Madras, and I'll be the TA for this course. So, like every other week, we shall be solving some sample problems together. Okay. So, without any further ado, let us hop in. So, we're looking at question number 1 of today's session. Read the question carefully, and once you have figured out the correct solution to the question, you can either unmute yourself and answer, or you can put in your answer in the chat box. Okay, so let's look into the question. The question says, which of the following types of equations are typically solved using the point Gauss-Seidel method? Is it option A, elliptic equations? Is it option B, parabolic equations? Is it option C, hyperbolic equations? Or is it option D, none of the above? So the fourth week of lectures, if you have gone through them, so they talk about different. We start discussing about the different solution techniques. Earlier we have been discussing the types of partial differential equations, how to classify them. Then we went on to see the different discretization strategies of those partial differential equations. And from week 4 onwards, we start looking into the different solution schemes. Once we have discretized the PDEs into set of algebraic equations, the next step is to strategize some methods on how to solve them. There are usually a large number of linear algebraic equations. How to solve them? So one of those solving methods is point Gauss-Seidel method, which we looked into. And the question is asking us which of the types of equations which are typically solved using the point Gauss-Seidel method. Is it option A, elliptic equations? Is it option B, parabolic equations? Is it option C, hyperbolic equations? Or is it option D, none of the above? So we already have, I guess, one response in the chat box, which is in favor of option A. We'll see if we get any other responses. Please try to participate in this, and if you have any doubts whatsoever regarding this, regarding anything else, please do not hesitate to ask. The point of having these sessions is to interact as much as possible, to have a open discussion. So the floor is yours. If you have any clarifications you want regarding the question, you can ask that as well. This is a very simple question to start off today's session. So which of the following types of equations are typically solved using the point Gauss-Seidel method? Is it option A, elliptic equations, option B, parabolic equations, option C, hyperbolic equations, or is it option D, none of the above? Okay, so let's have a look at the correct solution. It is indeed option A, elliptic equations. So we saw different kinds of elliptic equations. Primarily, they can be categorized into Laplace equations, and another type is Poisson equations. So different governing equations are of this form. For example, the most common example in this case is the 2D heat diffusion equation, which is the Laplacian of T equal to 0. Similarly, for different kinds of incompressible inviscid flows, we can get something like this: Laplacian of stream function or Laplacian of the velocity potential equal to 0. These are all elliptic type of equations, and more importantly, Laplace type of equations. Similarly, if we have a heat diffusion equation with some kind of heat generation within, with some kind of source term, so in that case it would be some function of x and y. This is the source term. This is a type of a Poisson equation. Similarly, if we have inviscid equations, incompressible inviscid equations, then they can be represented as so, where this is the vorticity. Okay, so all these class of equations, they can be solved using the point Gauss-Seidel method, which is similar to this. So let's say we take an example of a, you know, 2D heat diffusion equation which goes something like this. You know, the it's a partial differential equation, dou 2t dou x2 plus dou 2t dou y2 equal to 0. And if we discretize it using the central difference scheme, then we get something like, you know, I minus 1 comma j minus 2 I comma j plus ti, sorry, plus 1 comma j divided by delta x square plus a similar thing with y. So tij minus 1 minus 2 ti comma j plus ti plus, sorry, I comma j plus 1 over delta y squared equal to 0. Then we know that it can be further simplified into a linear equation which is something like this. 1 plus beta square ti comma j plus ti j minus 1 plus ti comma j plus 1 equal to 0. Here my beta is delta x over delta y, and here what we can do is we can use point Gauss-Seidel method to solve for this ti comma j in a iterative sense. Okay. So this was, you know, discussed in very much detail in the lectures. You can always go back to them and have a look. So I hope that clears things up. Any questions regarding this one, or, you know, any questions regarding point Gauss-Seidel method or elliptic equations? No, right? Okay. So we will move on. We will move on to question number 2 of today's session, which is asking us which of the following iterative methods is known for its simplicity but slow convergence. Is it option A, point Gauss-Seidel method, option B, line Gauss-Seidel method, option C, SOR method, or is it option D, Jacobi method? So read the question carefully, look at the options, and then try to figure out which one is the correct one. So the main things to focus over here are, it's a iterative method which is known for its simplicity but but slow convergence. So it's a simple method with a which is not very quick in its convergence, not very efficient, so to say. Does anyone know the full form of SOR method? Anyone? Don't hesitate. I mean, you can take a guess. It's okay to be wrong. No issues. So SOR method basically means successive over relaxation method. Okay, so we have one answer in favor of option C. Let's see what others have to say. So the question is asking us which of the following iterative methods is known for its simplicity but slow convergence. Is it point Gauss-Seidel method? Is it line Gauss-Seidel method? Is it successive over relaxation method? Or is it option D, Jacobi method? Okay, so we have one other answer in favor of option A, which is point Gauss-Seidel method. Let's see if we have any other responses. So these four are all different iterative methods. You have to figure out which one is known for its simplicity but slow convergence. Is it point Gauss-Seidel method? Is it line Gauss-Seidel method? Is it successive over-relaxation method? Or is it option D, Jacobi method? So really focus on this point here, slow convergence, not a very fast convergence. Okay, so let's have a look at the solution. The answer is option D, Jacobi method. So those of you picked out these other options, option A or C, or even if you think B would be the correct answer, then these would have been wrong because these are all, methods which give faster solution than this Jacobi method. But the real advantage of Jacobi method was its simplicity. Why? Because you know we figured out the values at the k plus 1th iteration or the current iteration, or you can say the new value of phi. It was found out entirely in terms of the values of the quantities at the kth interval or the kth iteration, the previous uh, iteration. So what you have to do is you have to save different arrays, one with the previous value of k and another one with the new values of k, and while calculating this one, only the values from this older array of phi are used, which one belongs to the kth iteration. It's not updated, which we can see in point Gauss-Seidel method or line Gauss-Seidel method, where uh, you know in these situations these are the k plus 1th iteration. In the k plus 1th iteration, we find this out using the values from the kth iteration as well as some updated values from the k plus 1th iteration. So that's why they lead to faster convergence. So this is the reason why Jacobi method is slower than the other ones, but it's more simple. It was one of the earliest developed methods to solve for you know in order to solve elliptic equations, but now it has been rendered obsolete because of its slow convergence. So this was the point to be focused on in the question. That's why the Jacobi method would be the correct answer. Okay. Any doubts regarding this one? Why it's Jacobi method and not any other one? No questions, right? Okay. So we will move on. We will move on to question number 3, which is what is the primary advantage of using over relaxation in iterative methods? Does it lead us to option A, more accurate solutions, option B, faster convergence, option C, greater stability, or is it option D, none of the above? So over relaxation is a you know technique quite widely used in CFD. It has some benefits. What is the primary benefit of using it? Is it option A, more accurate solutions, option B, faster convergence, option C, greater stability, or option D, none of the above? Take your time, there is no hurry. Try to think about it. What could be the primary advantage of using a over relaxation method? Okay, so we have one answer in favor of option C. Let's see what others have to say. Okay, another in favor of option B. So, okay, anyone else? Any other answers? What is the primary advantage of using over relaxation in iterative methods? Does it give us option A, more accurate solutions, option B, faster convergence, option C, greater stability, or option D, none of the above? Try to figure out the correct option, and once you have done so, you can put in your response in the chat box. If you have any things that you'd be like to be discussed on anything on over relaxation or iterative methods in general, please try to bring that up. We will have a detailed discussion on it. Okay, so let's have a look at the solution. The solution is option B, faster convergence. So faster convergence is the only reason why over relaxation methods are used. So the thing is, what is exactly done in over relaxation? So I have this phi pi comma j of k at k plus 1th iteration. So what we do is we take the values at the earlier iteration and then we add some correction to it. So this is a provisional value and this is the older value, and we multiply this with some over relaxation parameter omega. So omega here means over relaxation parameter, and this one here is the provisional value of phi, so we'll call it provisional phi, and this is somewhat equivalent to that in the k plus 1th iteration, right? Not exactly equal, it's equivalent to it. So think if this relaxation, not over relaxation, I'll call this relaxation parameter. So it can be over or sorry, so it can be over as well as under relaxed. It depends on the value of this parameter. So let's say if this is equal to 1, what happens then? So that simply means, okay, I'm forgetting about the I plus j notations for a bit. So this basically means this, right? So this one and this one would cancel out and it would simply give us this provisional value, which is true in cases where the relaxation parameter is equal to 1. Now try to understand the philosophy behind using this. This particular difference, this is some sort of a correction, right? This is a correction which is added onto the old value to get the new value. So if we increase this correction, we will approach the final solution more quickly. So how to increase that? We use a omega which is greater than 1. And these are the class of problems which are called over relaxed. So what this does is, with each iteration, we go from, k to k plus 1 to k plus 2 and so on. And what we are doing is we are actually trying to reach the final solution of it. So S means solution, the final solution. So as we are going through these iterations, if we somehow increase this correction a little bit, that would allow us to reach the final solution quicker. So reaching the final solution is what is called as convergence. And if we do it quicker or faster, so that's faster convergence, and that is usually obtained by using over relaxed uh, parameter. Now, does it mean that I can keep on increasing this omega indefinitely and get more faster and faster solutions? That's not true. So there is usually an optimum value of omega. So if I take this relaxation parameter here on the x-axis, and on the y-axis I take number of iterations to solution, then we usually get a curve something like this. And this particular value, okay, I'll draw this with a dotted line. So here where this is minimum, this is a optimum value of omega, which gives us the fastest convergence to the solution. Usually it is found out by trial and error method, but for some very particular scenarios, there is a formula to determine this omega optimum beforehand. Does anyone remember for which sort of situation it could be done? One example was discussed during the lecture. Any guesses, anyone? One case where there was a formula for this omega optimum. I don't remember the exact formula. Let me have a look at it. Yeah, so it was something like this: 2 minus 1 minus a divided by a. For what sort of a situation did we have this? For a rectangular domain with equally spaced grid. So delta x equal to constant, delta y equal to constant. This sort of a situation, we have a formula for the optimum over relaxation parameter. Okay. Any questions on this? No questions, right? Okay. So let's move along. We will move on to question number 4 of today's session. So, which of the following statements is true regarding under relaxation in iterative methods? It can lead to faster convergence than over relaxation. It can reduce the magnitude of oscillations in the solution. It is only applicable to nonlinear equations. Or is it option D, both A and B? So here we are talking about under relaxation, where omega is less than 1. Can be, it has to be greater than 0, but less than 1. So which of the following statements is true regarding under relaxation in iterative methods? Option A, it can lead to faster convergence than over relaxation. Is it option B, it can reduce the magnitude of oscillations in the solution? Option C, it is applicable only to nonlinear equations. Or is it option D, both A and B? Okay, we have one answer in favor of option B. Let's see what others have to say. If you have any questions regarding this one, please do ask. Any kind of clarification. So I have 4 statements here, or rather 3 statements here. And which of the following statements is true regarding the under relaxation technique in iterative methods? Does it lead to faster convergence than over relaxation? Can it reduce the magnitude of oscillations in the solution? Is it applicable only to nonlinear equations? Or is it option, or is it both A and B? That is both faster convergence as well as, you know, reduction in magnitude of oscillations in the solution. We have one response so far. Let's see if we get more. So which of the following statements is true regarding under relaxation in iterative methods? Does it option A, it can lead to faster convergence than over relaxation? Option B, it can reduce the magnitude of oscillations in the solution. Option C, it is only applicable to nonlinear equations, or is it D, both A and B? Okay, so we have another answer in favor of option D, that is both A and B. So let's have a look at the solution. The solution is, the correct answer is option D, that is both A and B are correct. So what happens in under relaxation? The correction that we were talking about. So this correction is sort of scaled down. So if omega is less than 1, the changes in each iteration is sort of reduced. It is sort of damped. Now what happens is, let's say we have something like this. So this is the number of iterations, and here on the y-axis, let's say we have the value of phi I comma k. So let's say we started off from some guess value, then we got some, we added some correction to it. It went like this, then it went like this, then it went like this. So it may happen so. So what this does is it ultimately slows down the solution. It goes to and fro, but never, approaches the actual solution, which is this. So this x-axis we will call as the correct solution. So the solution that we are calculating, it is going to and fro, up, above and below the correct solution, but it's never actually reaching there. So it may happen so. And in this situation, if we use an under relaxation technique, what it does is, let's say from this point to this point, we are going this much. Now, had we damped that down, had we used an under relaxation technique, so it might have not gone this far, and it only could have gone this far. In the next preceding steps, it could ultimately reach the exact solution. So this takes care of, such oscillations in the solution. So that's why option B is correct, and option A is also correct, because let's say if we had used over relaxation technique here, so in such a situation, had we used over relaxation technique, it would have further increased this magnitude of solution, magnitude of the, oscillations in the solution. So this is bad. We don't want this, and this would have gone on for forever. It would have taken a lot more time to converge in that case. So using an under relaxation in this case would have, damped down those oscillations, and that could have led to a faster convergence than over relaxation. So that's why option A is correct as well. So the correct answer to this question would be option D, both A and B. Does that make things clear? Any questions on this? Any questions, any suggestions any comment that you would like to make, please don't hesitate. I am more than happy to have a discussion on this with you. No questions, right? Okay. So we will keep moving on. We will move on to question number 5 of today's session, which is asking us which of the following iterative methods is better at handling non-uniform meshes? Is it option A, point Gauss-Seidel method, or is it option B, line Gauss-Seidel method? Okay, so we have one answer in favor of option B, line Gauss-Seidel method. Two answers in favor of option B. Let's see what others have to say. So this is question number 5 of today's session, which is asking us which of the following iterative methods is better at handling non-uniform meshes? Is it option A, point Gauss-Seidel method, or is it option B, line Gauss-Seidel method? So far, we have all the responses in favor of option B. Let's see if we get any other response. Okay, so let's have a look at the solution. The solution is option A, point Gauss-Seidel method. Line Gauss-Seidel method is not that good in handling non-uniform meshes. This is because of the methodology which is used. So basically, let's say we have a domain like this. What is done in point Gauss-Seidel method is that we go from point to point. Right? So let's say we have a grid like this. We go from this point to this point to the next point and so on. And we, you know, do this some row by row. Once this row is done, we go to another row, and then even then we pick point by point and try to find out the values at each point. Using the values in the neighboring ones, we use the updated values as well as some of the old values which are not found out in that current iteration. But what is done in line Gauss-Seidel is that one entire line is taken. So 3 points would be taken and they would be solved at once. Now, the issue which happens with non-uniform grids is, let's say we have one point here, another point here, another point here, like that. So in such a situation, if we try to take all of these and try to solve all of them together, the resulting equation becomes a bit more difficult to handle. So here in this case we have delta x and delta y both as constants. Let's say I'll call them C1 and C2. In this case, in a non-uniform grid, it's not so, right? In this case, these are not constants. So there could be points at uh, which are not distributed in a uniform which are not distributed with uniform spacing in between them. So that results in difficulties while using the line Gauss Seidel method, which takes multiple points at once and tries to solve them. Got my point?
Yes, sir.
So anything that you'd like to ask regarding this one? Any doubts? So we will move along. We'll move on to question number 6 of today's session. So this is asking us which one of these are not governed by elliptic equations. Is it option A, 2D incompressible inviscid flow? So different situations are given. So there are some governing equations to these physical problems. The what you have to figure out in this question is you have to figure out which one is not governed by an elliptic equation. So is it option A, a 2D incompressible inviscid flow? Is it option B, a 2D incompressible viscous flow? Is it option C, 3D incompressible inviscid flow? Or is it option D, none of these? Okay, so we have one answer in favor of option B. Let's see what others have to say. Read the question carefully. Okay, another answer in favor of option B. Which one of these are not governed by elliptic equations? Is it option A, 2D incompressible inviscid flow? Is it option B, 2D incompressible viscous flow? Or is it option C, 3D incompressible inviscid flow? Or is it option D, none of these? So far, we have all responses in favor of option B. Let's see if we get any other response. Okay, so all in favor of option B. Let's have a look at the correct solution. It is actually option D, none of these. Why? Let's look into the governing equation. So for the first one, 2D incompressible inviscid flow. How can we write down the governing equation for this? Can anyone help me? What is the governing equation for an inviscid incompressible flow in 2D? So we can write it down two ways. One of the ways is using a stream function formulation. So that goes as dou 2 psi dou x square plus dou 2 psi dou y square equal to 0. So this is how we can write this down. This is a uh, you know elliptic equation. That's very simple to find out and categorize. Now, okay, we'll come to option B later since you were guessing that this would have been the correct answer. Let's look at this one, 3D incompressible invisible flow. This is very simple, exactly like this one. We will write this down in this fashion. Okay, so one important clarification here. defining stream functions or streamlines in 3D is a bit more involved. So what we can do is we can switch to the other way. This can be, uh, you know, formulated using a velocity potential as well instead of using a stream function. It works both ways. So both ways would give you the correct governing equation. So for this 3D also we can do a similar thing. We can define a velocity potential and then take partial double partial derivatives in all the three dimensions of the flow. Simple, right? Nothing sketchy, and all of these are elliptic equations. Now, for a 2D incompressible viscous flow, why do you think that it would not be governed by an elliptic equation? What is the governing equation for this? Anyone? Governing equation for a 2D incompressible viscous flow. So this can also be written down using a stream function formulation. So we will have something like this in 2D, and this would be equal to an omega, which is the vorticity. So instead of being a Laplacian, this would be a Poisson equation. Now that doesn't mean that this becomes non-elliptic. This is still an elliptic equation. So that's why all three of these are governed by elliptic equations, and none of these would have been the correct answer. Does this clear things up? Am I making sense? If you have any doubts, please clarify them now, because since most of you were contradicting me in this one, or rather I am contradicting all of you. So I just want to make sure that I'm making sense here, and you're uh, getting where things were going wrong. Any doubts, any questions regarding this one?
No, sir.
Okay, so let's move along then. We will move on to question number 7 of today's session. So, which of these methods have more data storage requirements? Is it option A, Jacobi method, or is it option B, Gauss-Seidel method? So, while doing CFD of very involved, very complicated systems, there are two main things to take care of. One is the computational cost, the number of iterations which I'm performing, number of calculations that I'm forcing the computer to carry out. That is known as the computational cost. And the second thing is the data storage cost. So it may so happen that I'm using very less number of calculations, but on the other hand, I'm storing huge amounts of data in order to carry out those calculations. So that is also not a very feasible situation. So these are the two costs to keep in mind: computational cost and data storage requirement. So as far as methods are concerned, so we have two methods over here: option A, Jacobi method, and option B, Gauss-Seidel method. So which of these methods have more data storage requirement? That is what you have to figure out. Okay, so one answer in favor of option A. Let's see what others have to say. Option A once again. Alright, so Jacobi method and Gauss-Seidel method. Which one of these two methods have more data storage requirements? Option A once again. So all in favor of option A. Let's have a look at the correct solution. It is indeed option A, Jacobi method. So why does it have more data storage requirement? How did you get that solution? Like how will you defend your solution? Answer that Jacobi method has more data storage requirements. Why does it have so? Anyone? So all of you got the answer correct. I'm just asking why. It's a very simple answer. Come on. Don't feel shy. You can unmute and answer, or you can, type in chat box as well. That's up to you. Why does Jacobi method have more data storage requirement? All of you got the answer correct. Now I'm just asking why. You know, you can take a guess. Feel free to.
Just I guess it, sir.
Yeah, okay. Please go ahead.
Actually, no idea about it, but I guess that, sir.
Oh, okay. Any guesses why?
It's a matrix method, no?
Both are matrix method, but there is one inherent thing in Jacobi method for which it uses nearly double the data storage. So I'll say this. So storage for Jacobi method, it could be double that of Gauss-Seidel. Why do you think it would be? So basically what happens in Jacobi method, we have to use two different matrices. So one is the previous iteration. So it's a previous data. These are all at the kth iteration. And we have another new data, which is being calculated using the previous data, and this is the k plus 1th iteration. So we have to maintain these two different matrices, and these are all m cross n size matrices, where m are the number of points in the x-axis and n in the y-axis. So m cross n is the total number of nodes in the mesh. So we have to maintain two different matrices, and k plus 1th values are calculated in terms of all the kth values, and at the end of each iteration it is updated, like the previous data is then discarded and the new data is stored in the previous one, and then again as it moves to the next iteration, the again a new data matrix, there we store the value or calculate the values from the old one. So this loop goes on, but at all stages we have to maintain two matrices. But in Gauss-Seidel method, we have only one matrix, and we keep updating values as we go along. And during each calculation, we use you know data points which we have already calculated in this one. These are all belonging to k plus 1, k plus 1, and we use those from the older one as well, from k and k. So these are used to find out whatever point that we are solving for. So here we use only one matrix. So that reduces our data storage by half. Got my point? So this is the reason why Jacobi method has more data storage requirements. So it turns out Jacobi method is not so good, right? So it has slow convergence, as we saw earlier. Then it has more data storage requirement as well. So there are many disadvantages to the Jacobi method, which has led to making it almost obsolete. But it is still taught in CFD classes because of its simplicity, and it does have historical significance. It was one of the earliest techniques developed, and it formed the backbone of those techniques. Without Jacobi method, maybe Gauss-Seidel or other methods which we use today wouldn't have developed. So it has a significance in that sense. But other than that, there are lots of operational issues, which is why it's not used. Does that make things clear? Any questions on this or anything else? Please feel free to ask. This is so far been mostly one directional. I am talking anyway. So if you have anything in your mind, please speak up. Okay, no issues. So we will move along. We'll move on to question number 8 of today's session. So which of these methods have more data storage requirements? Okay, so same question but different options right now. Is it point Gauss Seidel method or is it option B line Gauss Seidel method? Okay, one answer in favor of option A. Let's see what others have to say. Another answer, another response in favor of option A. Another one. Okay, so all in favor of option A. Which of these methods have more data storage requirements? Is it point Gauss Seidel method or is it line Gauss Seidel method? So most of you are saying it's option A, point Gauss Seidel method. Now let's have a look at the solution. It is actually, I'm contradicting you again. It is option B, line Gauss Seidel method. And the reason for that is something that we discussed earlier. So in this case, there are, I minus 1 comma j, I comma j, then I plus 1 comma j. So in this case, there are multiple unknowns in each equation. So there are different there are multiple equations which are written down in this form. So it's kind of like this. I'm not getting into the actual coefficients here. This alpha, beta, gamma are just numbers equal to some delta, let's say. And these are, I'm giving a subscript 1 because there are multiple equations like this. So there will be a similar alpha 2, comma j, beta 2. Okay, in this case, we will move on with this. So we will be move along the different points. So I comma j, then I plus 1 comma j plus gamma 2 I plus 2 comma j equal to delta 2 and so on. So multiple lines and multiple equations. So this would lead us to having a matrix like this. So here all the phi's would be there. You get the point, right? So this vector would be like phi 1, phi 2, phi 3, phi 4, so on up until phi n. And here we will have those alpha, beta, gammas and so on. So this would be a whole matrix like this, and this would be equal to this delta I sort of a vector again. So here we have to, okay, so not delta. In this case, all these deltas are actually found out using, phi k's, which are known quantities. These are values from the previous iteration. And these are values of the current iteration. And here is a matrix here. Let's call this A matrix. Now, this also leads us to using two different matrices, one with the unknown values and one with the known values, whereas in point Gauss Seidel we have this only one matrix which we keep on updating each iteration. So here also the data storage requirement of line Gauss Seidel method would be more. Does that make sense? Any questions regarding this one? Did I could I properly explain why Line Gauss serial method has more data requirement than point Gauss serial one. If you have any doubts, please ask.
Sir, please repeat once again, sir.
Basically, what we have is, m cross n values of phi, right? So phi goes from 1 comma 2, sorry, 1 comma 1, 1 comma 2, and so on up until 1 comma n. Similarly, here we have phi 2 comma 1, and so on. Similarly, we have m comma 1 to m comma n, right? So let's say in point Gauss Seidel method, we maintain only one matrix like this. And at each iteration, let's say we have to find out the values of, something like at the I plus jth one, we will simply use the values at these 4 points. I minus 1 comma j, I plus 1 comma j, I minus 1 comma j, I plus, sorry, sorry. So this is I comma j minus 1, I comma j plus 1. So all these points would be in the kth iteration, from the kth iteration, and this one we will find out from the k plus 1th iteration, right? One second. Now, what happens in line Gauss Seidel method is that we solve for multiple unknowns at a single time using some other known values. So here all these deltas, these are functions of phi from the kth iteration, right? So here also we have to maintain two different matrices, one of previously calculated known values, this phi k, and these new unknown values at k plus 1, k plus 1th iteration. So that's why the data storage requirement increases a little bit. Here only one matrix is enough. Here actually two matrices are required.
Okay, okay, sir. Got it.
Any other questions? Okay. So let's move on. We'll move on to question number 9. What is the correct order of steps in TDMA? Okay, so first of all, what is TDMA? Anyone? TDMA, also known as
So, something tridiagonal matrix, Thomas
yeah,
algorithm.
correct. So it is tridiagonal matrix. Okay, I also forgot about what fuzzy. Give me a second. Algorithm. So TDMA, also known as Thomas algorithm. So it has a certain number of steps. I have given 3 steps here. You have to figure out what is the correct order of these steps. So step 1 is back substitution. Step 2 is forward elimination. Step 3 is conversion to upper diagonal matrix. And the options which we have are option A 1 2 3, option B 3 2 1, option C 3 1 2, or option D 2 1 3. What is the correct order of steps in order to execute this TDMA or tri-diagonal matrix algorithm? There is no hurry. take your time, try to figure out the correct solution here. What is the correct order of steps in TDMA or tri-diagonal matrix algorithm or Thomas algorithm? So, okay, we have one answer in favor of option B, 213. So, one is back substitution, two is forward elimination, three is conversion to upper diagonal matrix. And the options which we have are 1, 2, 3, 3, 2, 1, 3, 1, 2, and 2, 1, 3. So instead of looking at the options, try to figure out what are the actual correct steps. Then we can match it with the options which we have given in the question. So what is the first step in doing TDMA? First step, what is it? So, okay, to begin with, what is a tri-diagonal matrix? Can anyone answer? So this algorithm cannot be applied anywhere. We can apply it to only some specific matrices which are known as tri-diagonal matrix. Uh, how to identify a tri-diagonal matrix? What does it look like? So it basically has three diagonals. Like to say something?
The elements above the diagonal, the elements below the diagonal in the left hand side are zeros.
Okay, not all zeros. So basically there are three diagonals like this and rest are zeros. So basically we have something like this. So A1, A2, A3, dot 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 AN. Then we will have these B1s, but after that all will be zeros. Similarly, there will be another diagonal below it as well. So let me first do this one. So rest are zeros, rest are zeros. Similarly, there will be one below it. So C1 and all below will be zeros. So here also I'll have, sorry, C2, rest all zeros. C3, rest all zeros. Similarly, here I'll have Cn. There won't be a Bn because there are no elements over here. Other than that, all will be zeros. So basically, the matrix looks like there are three diagonals. One diagonal, which is this main diagonal. This A, the AIs are the main diagonal. Then I have this. Uh, this is called a super diagonal, and the one below it's called a sub diagonal. So this is what a tri-diagonal matrix is. Now what is the algorithm? In the algorithm, what is the first step? Any guesses? So the first one is to convert this to an upper diagonal matrix. Also sometimes written as U. So what is done is all these C's, the values of all the C1, C2, C3, C4, Cn, these are eliminated. So what we do is we take each row and then divide it by the appropriate or subtract appropriate values from it, so that all these c's disappear. So this is actually converted into a star I. I'm giving star because these values change up to an. All the c values disappear and the b values are also updated. Okay, so and in the equation there is a d matrix here, d2 to dn. This is also updated as a result of the row operations which we perform. So this is the first step. Okay, so I'll. Uh, okay, so first step we wrote down here. I'm writing down the second step here. The second step is the forward elimination. What we do over here is that we okay, so forward elimination is basically same as this step where you know all these updated values are calculated, rest are zeros, remember. So this is one of the main reasons why TDMA works, because a lot of the other values are zero. And the last step is back substitution. What we do here, okay, forward elimination means we are going from the first row to the second, uh, to the third, to the fourth, and so on, to the last one. So this goes on in a forward sense. Now, while back substitution, we start from the end. We say that, in this matrix, if you look at the last row, all elements are zero and we have only an, and this is equal to dn. So we put an equal to dn star, right? And then in the next equation, it would be something like an minus 1 plus, you know, let's say we are solving for some t over here. So t1 to tn. So tn minus 1. So tn an equal to dn. From here we can get tn easily. Both are known values. So dn by an would give us tn. Now in the next equation there would be tn an minus 1 plus tn an sort of a thing. So we have already found out Tn from the previous equation and we solve for Tn minus 1 using all these values. So in this way we build our way up. So we start from the nth row and go towards the first row. So that's why this step is called backward substitution. So if we come to this, so our first step would be conversion to upper diagonal matrix, then forward elimination, then backward substitution. So our correct order of steps would be 3, 2, 1. If we look at the solution, it is indeed option B, 3, 2, 1. Okay. Any questions on this? All right. So if there are no questions, we'll move on to last question of today's session. This is question 10. This is a match the following type of question, which is asking us, there are two columns given here. On the left column, we have different solution methods, and on the right column, we have certain disadvantages. We have to match the solution method with their disadvantages. So the solution methods are option A, over relaxation, option B, point Gauss Seidel, option C, line Gauss Seidel, and in disadvantages column we have non-uniform grids and irregular geometries. Option 2, may not converge. Option 3, matrices which are not diagonal dominant. So we have different methods in the left hand column and we have certain disadvantages which they may have in the right hand column. we have to match them with the correct one. So is it option A, A1, B3, C2? Is it option B, A3, B1, C2? Is it option C, A2, B3, C1? Or is it option D, A2, B1, C3? So you have to match the solution methods with their disadvantages. So let's go one by one. What disadvantage does over relaxation have?
May not converge.
May not converge. So just now, let's have a look at the last one, line Gaussian. This is something which we looked at in one of the earlier questions. What is the disadvantage of line Gaussian? In one of the earlier questions we looked at,
C2.
A is already 2, right? So may not converge.
Line Gaussian.
Yeah. So line Gaussian, does it have problem with non-uniform grids, or does it have problems with matrices which are not diagonal?
That is one. C1.
C1. So line Gauss-Seidel has problems with non-uniform grids and irregular geometries. So that leaves us with this last option, that is point Gauss-Seidel has problems with matrices which are not diagonal, which means, yeah, diagonal term, this being greater than equal to the sum of all other terms, j equal to 1 to n, j not equal to I, only the magnitudes of them. So if a matrix satisfies this condition, this is called a diagonal dominant one. Now point Gauss-Seidel has some problems with matrices which are not diagonal dominant. So that leaves us with the so the correct solution combination would be A2, B3, C1. Which option is that? Option C, right? So if we look at the correct solution, option C is the correct one, as we correctly found out. Any questions on this? Or anything else that we discussed so far today? All right. So if there are no questions, then that's all for today. We will meet again next week, and thank you for your participation in this. Looking forward to see you next week. Thanks.
Thank you. Thank you very much, sir.